This is section 7.5, the SSA condition, and then HL congruence. Okay, so we've got a couple more congruence theorems we're going to talk about. Both of these congruence theorems have special situations when they work. Okay, so they're not always going to work. They have to fit certain criteria to actually work, and I'll kind of explain that. So we had those four before that will work with any sets of triangles with that given information. These ones, you've got to have a little bit more information than just the sides and the angles. Okay, so for this first one here, SSA congruence theorem. So it says if two sides and the angle opposite the longer of the two sides in one triangle are congruent respectively to two sides and the corresponding angle in another triangle, then the angles are the triangles are congruent. Okay, so how this is different than the ones we've had before is the only way that this works is if you know which side is the longest, okay, or which side is longer than another side. So basically what you've got to have here is if this side here, so we know this side and this side match up with each other. If those sides are the longer of the two sides that they give, so like this side is bigger than this side and this side is bigger than this side, then we can use this, okay? And your longer one has to be opposite your bigger angle, so that also has to deal with those angles there, okay? So I'll write in here that those ones I highlighted, that one and that one, have to be longer than the other sides that they give us, okay? So you can kind of tell here, see how they did a capital S, a lowercase s, and then a capital A. When you do this, your capital S is your longer side. Then the next thing you've got to have is your shorter side, so a small s for your shorter side. And then opposite your longer side, you've got to have the angle. So that's why it's a capital A, because that's the angle that's the bigger one than, you know, some other angle, because we remember that our longest side is opposite our largest angle. So it's capital A there, and then angle is opposite our longer side. So of the two sides that they give us, we have to know that one of them is longer than the other, and we also have to know that the longer one is opposite the angle that they give us. Okay? If you notice here, this spelled backwards is a word that you probably know. I usually call this one the backwards theorem, okay, because it does spell that word backwards, and it does have special conditions to it. So if you hear me ever use the backwards theorem, I'm talking about this one because I'm not going to say that word there, but I call this one the backwards one. So if you ever hear that, that's what I'm talking about. Okay, so the other one we've got is dealing with right triangles. So in right triangles, if you remember from like Pythagorean theorem, you've got things that are called the hypotenuse and the leg. Hypotenuse is always the side that's opposite your 90. So you've got your 90-degree angle there, and the side opposite that is your hypotenuse, and then your other two sides there are just called the legs. With right triangles, the hypotenuse is always the longest of the sides. So your hypotenuse, in this case, would kind of be like what it is up here, the longest one. So if you know that this angle here is 90, and that's opposite your longer side, that's kind of like our backwards one here where we've got, you know, the bigger side opposite the bigger angle, because we also know here that this has got to be the biggest angle, because if this is 90, to split up the other two angles to be able to add to 180, they've definitely got to be less than 90. Okay? So that kind of goes along with this next theorem here, how we've got HL congruence theorem. So with that one, it's called hypotenuse leg congruence theorem. So it says if in two right triangles, the hypotenuse and a leg of one are congruent to the hypotenuse and the leg of the other, then the two triangles are congruent. So if we knew, say the hypotenuse here was like 3 and this hypotenuse was 3, and then we also had a side here that was 2 and this side was 2, then we could tell that those were congruent to each other. But you've got to have the side that is the hypotenuse, and we can tell that because it's opposite that 90 degrees. Okay, so these ones just have a few more extra rules to them, but they're those congruence theorems just like we had before. All right, so let's look back at our sheet here. So this first one, they want us to set up in a proof. They just kind of describe it slightly different than we usually see. So it says one set of rafters, basically wooden beams here, of a roof is designed below, so right here, and then it says rafters segment F to R, so that one there, and segment FA are the same length, and then it says explain why the beam going across the bottom, F to T, or I guess not across the bottom, the up and down one here, to the rafters perpendicular to the base, bisects this horizontal beam. Okay, so they're wanting to know if this is 90 here, why this cuts this in two congruent parts. Okay, so we can go back here to our the back side where I've kind of got this set up. So what they told us is they told us that F to R was congruent to F to A, and then also they told us, I think that this was a 90 in here. Alright, so walking through our different things here, the first one we've got is that FT is congruent to FT. So we are talking about this segment here is congruent to the same exact thing. Well, if we remember from previous sections, if it's something is congruent to itself, that's the reflexive property. So this is reflexive property of, in this case, of congruence. So reflexive property of incongruence when a segment is congruent to itself, which those segments are basically exactly the same, so reflexive. Next one here, we've got segment FR is congruent to segment FA. Well, they actually told us that in the problem, so it didn't say given, but they told us that in kind of the paragraph they gave us, so that second one is given there. And then this third one, so we've got triangle FTR and triangle FTA are right triangles with right angles at T. So this is also something they told us in the problem. Again, it's kind of hard to pick out of that paragraph versus just saying like given this, but that was a piece of information that they gave us. So now here, for the fourth one, based on all that information, we now can say that these two triangles are congruent to each other. So following my different things here, I've got, so this one's 90 here, this one is also 90 over here. I've got side, side, angle. Now this one, so it would be the backwards one, side, side, angle, but this also follows the certain situation like this one here where it's got that 90 degrees, right? So if this has got that 90 degrees, this is a hypotenuse, this is the leg, so this is actually going to be the HL theorem, or HL congruence theorem. There should be congruence in there. So HL congruence theorem, because we've got a hypotenuse, we've got a leg, and then we've got 90. So if you ever have that 90-degree triangle there, or a right triangle, clue in that it could be the hypotenuse leg one. Okay, so now we can say that those two triangles are congruent to each other. So now that we know they're congruent, now we can jump to that TR, so from there to there is congruent to TA. So whole thing is congruent to part of it's congruent. That's got to be CPCF. So CPCF theorem. So corresponding parts of congruent figures theorem. And then the last one, this one's kind of a tricky one here. So now that we know that those two are the same, we can say that this segment here, FT, is going to bisect that bottom side. This is kind of a hard one. This is definition of perpendicular bisector. Definition of perpendicular bisector. And in that definition, they basically just say if you've got a line coming through there, splitting it into two congruent parts like that, then it's going to be a bisector, and then also that it's meeting at that 90 degrees, so that's why it's a perpendicular bisector, but that's kind of a tricky one there. Alright, and then we've got our next example here, which they set up for us. So we've got that segment AB is parallel to segment CD. And then we've got segment AD, that top side there, is congruent to the bottom side, segment CB. And then segment AB is congruent to segment CD. And then we've also got that AC CD is 90, and we're supposed to prove that the top side and the bottom side are parallel to each other. So we're basically kind of trying to prove that it's basically a parallelogram. Alright, so going through here, first one, ACD is 90 degrees. Well, that was given to us up in the problem. Next one again is a given one where you've got segment AB is parallel to segment CD. Okay, so now this one, we are saying that angle CAB is also 90 degrees. Okay, so reason we know this, if I extend these lines out here a little bit, it's kind of like this, and extend, which one do I have to extend here? It's got to be this one. So this one is following that Z shape that we've had before. So be careful on this one. This one is actually the parallel lines theorem where it's talking about when you've got two lines and then those angles match up to be there. This one is parallel lines theorem versus alternate interior angles because you're starting with the sides are parallel and going to the angle parts versus the other way around. So that's why this one is parallel lines theorem. But it's really, really similar to the alternate interior angles one where it's following that Z-type shape there with those parallels. But it's just this one because we're starting with parallels versus starting with the alternate interiors. And then this next one here, since we know that those are both 90 degrees, now we can say they're right angles, and this is by definition of right angles. Because they tell us in that definition that if you've got a right angle, it's 90 degrees. It's a definition of right angles. Next one here is a given one again because we've got AD, that side is congruent to CB, that side, and then same with AB to CD. And now we're looking at our triangles here, so we are looking at CAD, which is the top triangle, and ACB, the bottom triangle. Well, again here, we've got side, side, angle, but the thing we've got to key in on is that we've got that 90 degrees in the corner here. So if we've got that 90, we've got a leg, and we've got the hypotenuse, this has got to be HL, congruence theorem. And you want to do that one versus SSA, or the backwards one, because it's got that 90 degree corner there. They're really similar to each other, but if it's got that 90, you've got to key in that that's the HL one. Okay, so then we've done a couple of these where you go from the whole thing being congruent to now one angle measure matches up to be congruent. So this is CPCF again, because our corresponding parts are going to be congruent to each other. And then the last one here, this one we are going from those angles matching up. So ACD, that one, better there, and ACB, that one. So again, this kind of follows our Z shape here. So since it does follow that Z shape again, this one actually is the alternate interior angles one. So this is alternate interior angles theorem. And this one is the one that actually uses that alternate interiors wording because you're going from the angles to that they're parallel, so that's why this one's alternate interior angles versus what we had to do for the other one with parallel lines theorem, because that one we started with parallel and then went to congruent or equal to each other. So that's kind of tricky there. Alright, so that is it for your notes. So you got that book page, page 410, 1 to 9, and 10 to 14 even.